Today we are going to begin our examination of limits. So we're going to start by determining a limit graphically. So our goal today or objective today is to determine a limit from the graph of a function. So let's take a look at the function on the left. We've got some limit notation. So we've got the limit as x approaches 1 of f of x. And we're saying that's equal to 3 because as we get arbitrarily close to the x value of 1, and we kind of zoom in on the graph, then we can see that our y values, our f of x values, are approaching 3. In the second example, we can approach 0, so we would say the limit as x approaches 0 of f of x. And so we would zoom in on the area right around the x values of 0, right here. But our y values, when we come from each direction, are still approaching the same value, which is 2, the same y value, which is 2. So the informal definition is that as x approaches some value c from both sides, if your y values become arbitrarily close to that single number, then the limit is that single number. It doesn't matter whether or not the function exists at that point. Okay, so we can see from the second example that f is undefined at x equals 0, but the limit still exists because from the left side and from the right side, both y values are approaching 2. So let's go through a couple of definitions and some notation. So we can approach limits from two different sides, from the right side and from the left side. From the right side is going to have this little plus right here. Okay, and what it means is that as x approaches a, that value of a, from the right side of the graph, or the right side of the a value, f of x, or your y values, approach some value g. You can also come from the left. You'll have a minus sign. And again, it means that as x approaches a, now this time from the left side of that a value, f of x, your y values, are again approaching g, some arbitrary number. We get a two-sided limit if your right-sided limit equals your left-sided limit and they're equal to the same number. Okay, so if your right limit equals your left limit, then the limit as x approaches a exists and is equal to L. L or G, doesn't matter, these are constant values for representing your y values. So now let's take a look at some examples and see how we're doing. So first we'll take the look at the limit as x approaches 2 of this absolute value function. So as we approach x equaling 2 from the left side and from the right side, our y values in both cases are approaching 1. So we say that the limit as x approaches 2 of f of x equals 1. That's different than asking what the value of f of 2 is. At 2, we have a hole, and we know that the y value is equal to 3. We can look at the limit as x approaches 5. Again, we'll come from the left and from the right, and here our y values are approaching 4. We can read the value of f of 0 straight from the graph. It's this point right here, so it's also 3. We can look at the limit as x approaches -1 from the right, from the left, and in both cases your y value is approaching 4, and f of -1 is 4. So we need to consider what the difference between the questions A and D are, all right? And what we need to understand is that A is asking what f of x or your y values are approaching. D is asking what f of x actually equals. Okay, and in this case they're different because of the hole. We can see in examples C and F that if there isn't a hole, the limit as you approach the value and the value of the function at the same spot are equal. Sometimes that happens and sometimes that doesn't. All right, so let's continue on. Let's blow this up a little bit, make it a little easier to see. There we go, perfect. All right, for example number 2, we have another piecewise function. This time we want the limit as x approaches 1 from the left. So from the left means values to the left of 1. So we're approaching in this direction. And when we approach in that direction, we see that the y value is roughly equal to 2.5. When we approach the limit as x goes to 1 from the right, then we're coming from the right side towards x equaling 1, and our g of x function is now approaching 1.5. We can also look at limits as they approach negative infinity or positive infinity. So as we approach negative infinity, we're headed out in this direction on the graph, and we can see that the graph will continue in a negative direction and eventually hit negative infinity. We can look at positive infinity, headed out that way, and this function is constant, so that would be 1.5. We can also read the values from the graph. G of 1, here's 1, is 2.5, and G of -5, there's our x value of -5, is probably equal to -0.5. Things we should consider are, does the limit as x approaches 1 of f of x exist? And the answer is no, because the right limit does not equal the left limit. When we look at A and B, we have two different values for our g of x function. All right. Let me know if you have any questions about that before we move on to the next example. All right, so for our next example, we're going to look at behavior around vertical asymptotes. So this problem is asking us for part A, the limit as x approaches 2 from the left. So for values that are to the left of 2. So we're headed in that direction. And we can see that as we get closer to this x value of 2, we are headed towards positive infinity. Part B is asking, what's the limit as we approach 2, as x approaches 2 from the right? And again, our y values or h of x values are headed off towards positive infinity. Because these values agree, we can say that the limit as x approaches 2 of h of x exists, and it's equal to infinity. But we also know that at 2, the function does not exist. We have a vertical asymptote. So limits and existence, in terms of function existence, are different. All right, and then for E, we want the limit as x approaches negative infinity. So we're headed off in that direction. Looks like it's approaching 0. And the limit as x approaches positive infinity will also be 0. All right, so we want to remind ourselves that the limit as x approaches 2 of h of x, not g of x, so let me erase that for you. Exists because the right limit equals the left limit. And they equal the same value. All right, last example. We have this oscillating function. So we want the limit for the first part as x approaches 0 from the left. So we're coming in this direction. And it appears that t of x equals 1. Then it asks us for the limit as x approaches 0. So we need to check from the right. As we approach from the right, it's also approaching t of x is also approaching 1. So the limit as x approaches 0 is 1. But things get a little more complicated as we head out to infinity. So if we head out in this direction, we see that this function continues to oscillate between -1 and 1. And because it's not closing in on one value, the limit does not exist because it's not approaching one single value for your y values. The same thing is true as you head towards positive infinity. Again, this function continues to cycle between -1, 0, and 1 and is not approaching one single y value, so it does not exist. Okay, so just to remind ourselves quickly and take some notes, the limit as x approaches infinity of t of x and the limit as x approaches negative infinity of t of x do not exist because your y values are not approaching one single value. All right, let me know if you have any questions.